Hello and welcome to the channel. So let's find the parity of this scary number having 1 million in the exponent. Decide whether it is even or odd. The lower square brackets stand for the integral part, the floor of a number, defined as the greatest integer not exceeding the given number. In other words, rounding to an integer is always performed downward to the lesser number. To be honest, the original expression was much more humble, which was alright for year 1975, while nowadays you can bring up Wolfram Alpha and for the power of 100 get the answer immediately using the following instruction. However, with the power of 1 million, even Wolfram Alpha can't help. What is really remarkable here, number 44 before the square root remained unchanged. However, if 2022 is increased to 2026, the number before the square root must be incremented for consistency. This may provide a good clue to pause the video and solve on your own. So, what is special about number 44? We know that it is related to the number under square root. Indeed, there is a strong feeling that number 44 is very close to the square root of 2022. Let's see if such a guess is correct. 44 squared is 1936, which is rather far from what we expect. However, 45 squared is 2025, which is already greater than 2022. So we can write that 2022 is greater than 44 squared and less than 45 squared. Since square root is a monotonically increasing function, square root of 2022 is more than 44 and less than 45. This means that 44 is the integral part of the square root of number 2022. Now, as the reason of having 44 has become clear, we can formulate the problem in general terms. Take number p defined as a plus square root of b, where b is a positive integer and a is the integral part of the square root of b. It can be easily seen that a is also a positive integer. We also need a to be different from the square root of b, because if a is equal to the square root of b, then p is just 2a. Therefore, p is not merely an integer, it is an even number. Therefore, p to the power of n is even for any positive integer n, and the problem is solved. So, we assume that a is not equal to the square root of b, but a is the integral part of the square root of b, so it cannot be more than the square root of b. Therefore, a must be less than the square root of b, while the next number a plus 1 is greater than the square root of b. Subtracting a from all three sides of this double inequality, we find that the square root of b minus a is more than 0 and less than 1. Number square root of b minus a is in fact the fractional part of the square root of b. However, we will deal with its opposite. Number q equal to a minus square root of b. We see that numbers p and q differ only in signs before the square root. Such numbers are called irrationally conjugate. If we raise conjugate numbers to the same positive integer power, we get numbers conjugate to each other. Someone may take it for granted, but since that can be easily proven, let's prove it. Statement 1. If n is a positive integer, then p to the power of n equals c sub n plus d sub n times the square root of b, and q to the power of n equals c sub n minus d sub n times the square root of b, where c sub n and d sub n are positive integers. Of course, it can be proven using Newton's binomial formula. However, I find it simpler to prove by induction. For the base case, take n equal to 1. Power 1 of a number is the number itself, so we assume c sub 1 to be a and d sub 1 to be 1. Both c sub 1 and d sub 1 are positive integers, the base case is complete, and we move on to the step case. Now we assume the statement to hold for n equals k, and get the formulae for p to the power of k and q to the power of k. Let's see what we will get for the power of k plus 1. P to the power of k plus 1 is p to the power of k times p. For p to the power of k, we use the formula from the induction hypothesis, while the second term p is just a plus square root of b. Next, we distribute and group separately the terms not containing square root of b and terms containing the square root. In the similar way, we get the expression for q to the power of k plus 1, which differs from the previous expression only in sign before the second term. So both p to the power of k plus 1 and q to the power of k plus 1 have same expression in the first bracket, which we assume to be c sub k plus 1, and same expression in the second bracket, taken as d sub k plus 1. Since a, b, c sub k and d sub k are positive integers, c sub k plus 1 and d sub k plus 1 are positive integers as well, the only thing remained is to express p to the power of k plus 1 and q to the power of k plus 1 in terms of c sub k plus 1 and d sub k plus 1. We obtained exactly what was needed to complete the step case, so the statement is proven. Can you guess what I'm going to say? Try to complete on your own. Let's add up the expressions for p to the power of n and q to the power of n. The terms containing square root are cancelled out, so p to the power of n plus q to the power of n is just 2 times c sub n. By subtracting from both sides the sum of q to the power of n and 2 times c sub n, we get p to the power of n minus 2 times c sub n equals minus q to the power of n. It's time to get rid of q to the power of n by replacing it with something easier to deal with. First, we replace q with a minus square root of b, then represent a minus square root of b as negative 1 times square root of b minus a, and replace the power of a product by the product of powers. It was proven earlier the square root of b minus a is more than 0 and less than 1. However, if a number is strictly between 0 and 1, any positive power of it is also strictly between 0 and 1. So we can write the square root of b minus a to the power of n is more than 0 and less than 1. Let gamma sub n denote square root of b minus a to the power of n. So gamma sub n is more than 0 and less than 1. I decided to use a Greek letter to emphasize that gamma sub n is a fractional number. Now we can write that q to the power of n is negative 1 to the power of n times gamma sub n. And let's substitute the expression for q to the power of n into the formula for p to the power of n minus 2 times c sub n. Since q to the power of n appears with minus, the power of negative 1 must be incremented. Let's copy the formula for p to the power of n minus 2 times c sub n to the top, along with the inequality for gamma sub n. Now we can clean the page and consider separately odd and even values of n. If n is an odd number, the power of negative 1 is even. Therefore, gamma sub n appears with plus sign. Given the inequality for gamma sub n, we get p to the power of n minus 2 times c sub n is more than 0 and less than 1. By adding 2 times c sub n to all parts of the double inequality, we find out that p to the power of n is more than 2 times c sub n and less than 2 times c sub n plus 1. But c sub n is an integer. Therefore, 2 times c sub n is an even integer. It is less than p to the power of n, while the next integer, 2 times c sub n plus 1, is greater than p to the power of n. This means that the integral part of p to the power of n is exactly 2 times c sub n, and therefore is an even number. Now let's assume n to be an even number. In this case, the power of negative 1 is odd. Therefore, gamma sub n comes up with a negative sign. Since gamma sub n is between 0 and 1, negative gamma sub n is between negative 1 and 0. Therefore, this time p to the power of n minus 2 times c sub n is greater than negative 1 and less than 0. Again we add 2 times c sub n to all parts of the inequality, and find out that this time the integral part of p to the power of n is 2 times c sub n minus 1, while such a number is odd. We see that the integral part of p to the power of n always has a parity opposite to the parity of n. Given that p is a plus square root of b, we can write statement 2. For any positive integer n, the parity of the integral part of a plus square root of b to the power of n is opposite to the parity of n. Now let's get back to our case, where a equals 44 and b equals 2022. But what is really important for us, n is an even number. Therefore, the whole expression is an odd number. We've got the answer, and this is the end.